my lovely, strong, wonderful, hardworking, awesome AP students. It is the last week before Thanksgiving break. You can do this. I miss you tons, but use this week wisely. And let's learn about concavity and points of inflection. Last week, we talked about concavity and what it means to be concave up and concave down. So remember, if you're concave up, it's like a bowl shape, and concave down is like a rainbow shape. So here we've got like a concave up situation happening, and here we've got a concave down situation happening. Okay, so what we're going to talk about now is points of inflection. And points of inflection are the place where your concavity changes. Okay, so it's kind of like the equivalent of a minimum or maximum. Like that's where the increasing and decreasing changes, right? This is a point of inflection is where the concavity changes. So it looks like it's happening somewhere around here where we stop being this bottom part of the hill and start going into the bowl shape, or in other words, stop being concave down and start being concave up, okay? The way that we're gonna find that algebraically is we are going to find our PPOIs, which is potential points of inflection. And those happen where the second derivative equals 0. Okay? So they're very similar to our critical points. Remember, our critical points is where we change from increasing to decreasing, and that's where the first derivative equals 0. Potential points of inflection is the same idea. We're going to look for where the second derivative equals 0. Example 1 on your note card asks us to find where this graph is concave down. So we are going to use the same process that we did to find our critical points, except now instead of the first derivative, we take the second derivative. And all that means is we literally take the derivative twice. It's the second derivative. So let's take the derivative the first time. So my first derivative would be 12x cubed minus, I would have 30 plus 18, so minus 48x squared plus 48x, and then my constant would disappear when I take that derivative. That's the first derivative. I want the second derivative. So I'm going to take the derivative again. Here we go. And same thing, we would have 36x squared minus, that would be 80 and 16, so 96x plus 48. And to find the potential points of inflection, I want to see where the second derivative equals 0. Again, we're trying to figure out where our concavity is changing so we can figure out when it is concave down. So I'm going to solve this by factoring it, and I can take out a 12 to make my life a little bit easier. So then I would have 3x squared minus 8x plus 4 is equal to 0. So now I'm going to try to factor this. I know my only choices here are 3x and an x, and I could get 12 and 4, so I could put a 4 here and a 1 here, right? Nope, I need 2. Need a 2 here and a 2 here. So I'd have 6x and 2x would make 8x if these are both negative. So I know that that is correct. So then I know that x must equal 2/3, right? If we set this equal to 0, or x is equal to 2. So these are now my potential points of inflection. And we're calling them potential because we don't know if the concavity is changing there for sure, but we're gonna check and see right now using our number line. So let's put our number line here. And we need to put our potentials on there. We've got 2/3 and we've got 2. And I want to see where the second derivative, because I'm talking about concavity, so second derivative is, we're seeing if it's positive or negative. So I want to plug it into this right here. And sorry, this should technically have that 12 still there. So I'm going to plug in something that is less than 2/3, so like 0. I would have a positive times a negative times a negative, which would give me a positive there. If I plug in something in between here like 1, I'd have a positive times a negative, which would give me a negative. And then here I would have something bigger than 3 would give me all positives. So I must have something that is concave up. Positive means concave up. Negative concave down. Positive concave up. And then we go back, look and see what this question was asking. It wanted the concave down interval. So we would say that it is concave down from 2/3 to 2, because the second derivative, oops, sorry, running out of room, is less than 0. It was negative there. Sorry, it's a little squished there. So we're saying that we wanted to find the negative interval because concave down is negative, just like it would seem so intuitively, right? Negative down. So 2/3 to 2 because the second derivative was less than 0. That's how we know where something is concave down. Number 2 on your note card asks us for 2 things. It wants us to determine the intervals where f of x is concave up and it wants us to find points of inflection. So we can't figure out where it's concave up until we find points of inflection anyways. We do that by taking what derivative? The second derivative, but we have to do the first derivative first. So this one, the derivative of sine is cosine, and I don't need chain rule because this is just a simple x in there, but I should always check, and the plus 2 goes away. So that's my first derivative, but I want the second derivative because I'm thinking about concavity as second derivative. So derivative of cosine is negative sine, and again, no need for chain rule. All right, now I need to figure out where this equals 0. So I need to think about my unit circle here. Right? I know that the places that contain 0 are these points here. This one I have 0 or 2 pi. This one I have pi over 2. This is 1 pi, and this is 3 pi over 2. And then I know that this point, thinking about graphing, I went to the right 1 and up 0. Here I went to the right 0, up 1. Here I went to the left 1, up 0. And here I went to the left none and down 1. Okay, so I want to see where the sine is equal to 0, and the negative doesn't affect us here because we're talking about 0. Okay, so where the sine is equal to 0, sine comes second, so that would be at 2 pi or at pi, but this is a circle. It goes around forever and forever and forever. So after 2 pi comes 3 pi, and notice my interval here. It asks for from 0 to 3 pi. So actually all of the places that it would be equaling 0, my potential points of inflection, I would have it at 0, I would have it at pi, I would have it at 2 pi, and I would have it at 3 pi. Okay, I'm going to erase this so that I can make it a little bit bigger, and then we'll continue. Okay, now we're going to have to think carefully about our unit circle in order to fill this in. So my interval starts at 0, so I don't really have to consider anything to the left of 0 here. So, but I am going to consider between 0 and pi. So at pi over 2 up here, my sine, I had 0, 1, so my sine is positive up there, right? So I'd have a positive here. Then between pi and 2 pi, down here at this point, I would have a negative sign, right? Because I went 0, negative 1. So this would be negative, and then that pattern is going to repeat as we work itself around the circle. Oh, but again, our interval ends at 3 pi, so I don't really care what's happening here. Okay, so be careful with that. All right, then, so our question asked us, where does concave up? So for part A, we want our positive intervals as concave up. So we would say it's from 0 to pi and from 2 pi to 3 pi. And then where it says justify, that's where we write that because the second derivative of x is greater than 0. We want concave up. Okay, so that's all we need for justify. That's enough justification. Then for part B, points of inflection are where it's actually changing concavity, which was happening to us every time. So our points of inflection in that interval would be at pi and at 2 pi. So for part B, we found that our concavity was changing at pi and at 2 pi. It does ask us for the points of inflection. So when it asks us for a point, it's actually not expecting something like this. It should be pi comma something and 2 pi comma something. So how do we figure out the something? Plug it back in to our original. For their points, we always want to go back to the original. So if we go back to the original, that was at, so we'll do f of pi, would be sine of pi plus 2. And we know that the sine of pi was this one over here, right? Which was 0, so it would be 2. So one of my points of inflection would be pi comma 2. And then 2 pi was also 0, and we also had 2, so that would also be 2 pi comma 2. Example 3. Determine the intervals where it is concave down and concave up and state the points of inflection. So all of those pieces, you've got it. We're going to take the second derivative. Before I even take the derivative, I've got a radical, and we have done this so many times now, hopefully it's starting to sink in, that a cubed root is the same as a 1/3 exponent, which makes it easier for us to take the derivative. So we're going to take the first derivative. I'm going to have to use chain rule here, take the derivative of the outside, keep the inside the same, this would be the negative 2/3, times the derivative of the inside, which would be just 2. Okay. I'm going to rewrite this, just multiply, and I'm not going to write this as radical because I have to take the derivative again. So I'm going to leave it like this, and take the second derivative now. I just multiplied that 1/3 times that 2. Forgot to narrate that, sorry. All right, now I'm going to multiply this. So I've got negative 4 over 9. When we multiply fractions, we multiply the numerators and multiply the denominators. 2x minus 1, same thing. We're using chain rule, so outside, keep the inside the same. This, I'm going to do negative 2/3 minus 3/3, which would be negative 5/3. And then times 2. So I would get negative 8/9, 2x minus 1 to the negative 5/3. All right, just rewrote that at the top there to give us some more space. And now I'm going to rewrite this using my fraction exponent rule. So the negative means move it down to the bottom, and then that must be the cubed root there. Oops, I've still got that 9 in the front from this denominator. Then the cubed root's coming from the 1/3, and then I would have 2x minus 1, and that whole thing is being raised to the 5th. All right, now this works the same way as critical points. I need to know either where the numerator equals 0 or where this whole thing is undefined, or where the denominator equals 0. And this looks messy, but the only way that this is going to equal 0 is if what's inside here equals 0. So really we just need to think about what makes 2x minus 1 equal 0, which would be 1/2. So now I can draw my number line here. I've got 1/2. I want to plug this into the, whatever my test numbers are, into my second derivative, because I'm testing for concavity. If I plug in 0, I would get a negative. Cubed root of a negative would stay negative, and then to the 5th power, it's an odd power, so that would also stay negative. But this up here is negative 2, so overall I would get positive. Okay, pause that there and work it out if that went too fast for you. Okay. Then 1, if I plug in 1 here, I get a positive, but I have a negative divided by a positive is a negative. So this question asked me, where does concave down? So down would be where it's negative, right? So we would have from 1/2 to, I don't have an interval or anything, so it'd be from 1/2 to infinity. And then up would be from negative infinity to 1/2 then. And points of inflection, I only have one that's at that 1/2. It is changing, so it is a point of inflection. And now I need to plug it back into the original. So going back to my original here, I want to plug in 1/2, and I would get 0, right? That would make 0 there. So my point of inflection must be at 1/2 comma 0. So again, remember when we find our points of inflection, we plug it back into the original to find that y value, not into the derivative. And now we're going to put together a lot of things that we've learned throughout the year. This is asking for the equation of the line tangent. So immediately when you see tangent, you should be thinking, oh, I'm going to take the derivative. But this says at its point of inflection. So I need to take the second derivative. So first derivative, I would have 3x squared plus 6x. The 2 would go away. Second derivative would then be 6x plus 6, and I want to set that equal to 0 in order to find my point of inflection. So x would be equal to -1. Okay, so now, think carefully about this. I have y minus y1, because I'm writing an equation, equals the slope of x minus x1. Okay, so my x1 is what I just solved for. That goes right here. I need to find my y1, and I need to find my m, right? So my m is my slope. That comes from my second derivative here. So I want to plug -1 into my, comes from my first derivative, right? The slope is the first derivative. So I need to plug -1 into my first derivative to find that m, which would then be, I would have 3 times +1 minus 6, which would be -3, okay? So -3 would be my slope then, so that would go here. I would have x minus -1, so that'll become x plus 1. So all I need left is my y1, and my y1 comes from my original, right? I want the original output for y1. So if I plug in -1, I would have -1 plus 3 plus 2, which would give me 4. So the equation of my line is y minus 4 equals -3 times x plus 1. Okay? So think very, very carefully about where each of these pieces comes from when you're plugging that -1 back in. I need the second derivative to find the point of inflection. Once I found that, that was my x1. To find my y1, I plug into the original, and to find my slope, I plug into the first derivative. All right, so all those pieces coming together to make our lovely equation of the tangent line.